Okay, so today's objective is to be able to actually use our logarithms, and we're going to specifically use these to help us solve exponential equations. So, really just diving into example problems today, because we're going to harness a lot of skills that we've used before. And the steps for solving these different equations: first, we're going to isolate the exponential expression. That means getting it all by itself. Then we'll rewrite our problem in logarithmic form, and we can then easily solve for the unknown variable. One thing to note is we want to wait until the end to evaluate the logarithm. That way we're not dealing with a bunch of nasty decimal numbers in the middle of our problem. So if we look at example one, it says isolate the exponential expression. We don't actually have to do that here. It's already done. That means we have a base, we have an exponent, and we have an answer. So we are isolated in that case. We don't have to worry about that problem. I'll put a check mark next to 1. Then, to rewrite this in logarithmic form, I'll do this step in blue here. We are going to write it as our log base 6, looks like of 51, equals x. And in this case, there is no need to do anything with that third step solving because x is already all alone. So that with that rewritten equation, we can kind of go into our Desmos here, calculate it out, because we will not be able to do log base 6 of 51 in our head. Log base 6 of 51 gives us 2.194. So that will be my answer here, where x equals 2.194. Again, rounding to 3 decimal places today. So moving on to example 2, we might get a little more complex in our problem. Notice how up top here, that entire exponent has some stuff going on with it. Okay, so when we don't have to worry about isolating the expression; it's already isolated. So we can just jump to rewriting in logarithmic form. I got log base 2 of 6, and that entire exponent here has to move to the right side of the equation. Right, so we get k plus 6 on the right side. That's our entire exponent, so it all shows up on the right there. So rewriting in log form is done. And now this is where we're going to need to solve for our unknown variable. And that means k, we want to get k all by itself. So I do that, I subtract 6 from both sides. Subtract 6 from both sides. I am, again, waiting until the end to evaluate the logarithm. So what happens here is I get log base 2 of 6 minus 6. That equals k. I have k all by itself. So then what I can do is I can take this entire expression that we have on the left side, log base 2 of 6 minus 6. I can throw that in Desmos here, log base 2 of 6 minus 6. And then we get a nice clean answer, negative 3.415 for what k is equal to. K is equal to negative 3.415. Just double check that I translated that correctly. All looks good. Now for example 3, example 4, a lot more complications going on with our problem. And the first thing to note is that our exponential expressions over here are not alone. They are not isolated. There's some other stuff going on with it in both problems, right? We have the plus 3 happening on the left, and we have multiply by 2 and add by 1 happening on the right. So we need to isolate those things first. In example 3, it's just moving that 3 over by subtracting it. So if we do that, we get 9 to the n plus 10 equals 81 minus 3 is 78. Now, since I have my exponential form isolated, I can rewrite as a log. So I go log base 9 of 78 equals, and it's going to be the entire exponent here, n plus 10. And then I want to get that n all by itself, so I'm going to subtract 10 from both sides, subtract 10 by both sides. I can't combine that log with the 10, so it's just going to be kind of written out as if they were unlike terms. Log base 9 of 78 minus 10 equals n. Now I have a nice expression here on the left that will give me what n is equal to. I go into Desmos, log base 9 of 78 minus 10. That gives me my answer, negative 8.017. So n equals negative 8.017 as our answer. Now, example 4, kind of similar approach, a little more complicated because we have two things happening to our exponential. We have it multiply by 2, we have it subtract by 1. So we should move that 1 away first. We're going to add 1 to both sides, add 1 to both sides. That leaves us with 2 times 4 to the x equals 128. Now we need to divide 2 from both sides to get that exponential all by itself. Divide 2, so now we get 4 to the x equals 128 divided by 2 is 64. And actually, this might be one you just be able to know right off the bat, but I'm going to rewrite it in log form anyway. Log base 4 of 64 equals x. And if I evaluate that one, it should give us 3, because that is one that we can do in our head. And yeah, bingo, it does give us 3 as our answer. So in this case, x equals 3. So another thing I want to point out, anytime that we are solving, I have a typo up in here. It's not polynomial equations. We are solving equations graphically, any sort of equation. Okay, we can plug each side of the equation in Desmos to separate functions, locate the intersections, and then find those x values. So if I go back to, let's do that example 3 here. If I take this 9n plus 10 plus 3, I plug it in as one function, f of x equals 9 to the, and I guess I'll have to do x plus 10 because that's our input there, plus 3, and then go in here as well and set my second function. I'll do g of x equal to 81. If I kind of zoom out and find that intersection there, boom, we have one. I can click on it, negative 8.017, and that does indeed match what we got as our answer down here, negative 8.017. All right, last thing, seeing how we could apply this to word problems. So in example 5, a $100 deposit is made into a bank that pays 12% interest per year. The money in the account A can be represented with the following function. And this is something that we used to build up, right? There's an initial amount, 12% growth gives us that 1.12, and we're raising to the t. So where t is the time in years, and we're going to try to answer the question, how long will it take the account to reach $2,000? So if we're working on that, okay, we don't know what t is. Normally we would plug in t and we would solve for a. However, we are actually solving for t in this case as our final answer. So t question mark, but we know that a is equal to 2,000. So what I'm going to do is I'm going to rewrite this equation here. I know 2,000 is what my a is equal to. That equals 100 times 1.12 to the t power. And now we can use our logarithms to solve for t. So I need to divide each side by 100 to get that exponential all by itself. So I get 2,000 divided by 100 gives me 20. Equals the 100 and 100 cancel out, so I just get 1.12 to the t power. Then if I rewrite this in logarithmic form, okay, I get log base of 1.12 of 20, and that equals that t there. Then I just have an expression I can plug into Desmos and come up with that time. So go down here, log base 1.12 of 20. And that should tell me what t is. It looks like 26.4 years is our answer, 26.4 years.